Hi guys, hope all of us are doing great. My name is Ernest, and this is the Ernest Sciences and Mathematics TV channel. Today we are going to look at one of the reactions which basically falls under the broader category of addition reactions in organic chemistry. And this is going to supplement our first video that we had done on hydration reactions, where basically we say that hydration reactions is one of the addition reactions that occur whereby water molecules is added or rather water molecules added across a double bond. That is a carbon-carbon double bond functional group. And in this case, we said that this particular kind of reaction occurs under the condition of a strong acidic aqueous solution. Now, for our case today, we are going to see one of the ways in which we can be able to represent this kind of a reaction, that is halogenation reaction, which basically entails which basically is a simple organic reaction that we're going to see the halogen molecules trying to interact with the carbon-carbon double bond functional group. And in our general case now, we are going to use our first illustration that we have done, which basically consisted of a double bond, which is a carbon-carbon double bond interacting with a halogen, whereby we had said that this basically can represent a halogen from the glass for chlorine, bromine, and iodine. So in this case, these are the specific ones that we're going to particularly consider in this case. So I'm going to pick 8 of them in my various illustrations to try and demonstrate how this specific reaction is going to take place. And therefore, from this kind of a reaction, this is going to involve the breakage of the pi bond, and then there's a formation of two sigma bonds, which are going to involve the carbon from the alkene functional group, of course, and these halide molecules. So this, in our first case, we said that this is going to form what we refer to as a physenol halide. And this basically involves the formation of a dihalide with this particular either bromide, chloride, or iodide molecules, or rather atoms joining to adjacent carbon groups. So in this particular case, we are going to look at first some of the few examples that we can be able to use to illustrate this. And then we are going to look at, in collaboration with that, the reaction mechanism which is going to accompany this. Now, in this particular case, we had mentioned the case of a preference, but in this sense whereby we're going to use, this is a dihalide with similar molecules, therefore we are just going to restrict ourselves with the reaction mechanism, and maybe the concept of preference is not going to take a place or play a role in this particular case. So if I may give a specific example for this, we have this specific molecule, which is of course an alkene functional group, and then we are going to have this concept of bromination taking place, and this is going to result to the formation of a dihalide, which is going to be represented as this. So whenever I have those particular representation, I can decide to put a methyl group, but in this case I'm just going to illustrate them using that I presume that we are going to understand, and then later we're going to see the particularly the preference and the orientation of these particular molecules. We have discussed some of this in our introduction to stereochemistry, but I'm just going to give them as rough illustrations in this particular case, just to have that one, or just creating an emphasis in that particular case. Now, if we consider a reaction whereby we have an alkene functional group, which is going to react with this bromide, or rather bromine, and therefore I'm just going to have this illustration given as such. So I'm just putting this space so that we can just explain it from there. We said that we can be able to explain this particular halogen, which is a diatomic molecule, using that particular bond to show the bonding in between them. So in this case, whenever this particular halogen is going to come closer to the double bond, which is an alkene functional group, we're going to see that the interaction between this electron-rich species and this one is going to cause a repulsion effect in this particular halide molecule. And therefore, we are going to have this aspect of polarity whereby there's going to be a partial positive charge at this specific point and a partial negative charge at that specific point. This results from the repulsion of electrons from this particular molecules towards this other end of this bromide part, and therefore this is going to form some kind of an electrophile, therefore which is going to interact with this electron-rich part of the alkane functional group. Therefore, the subsequent reaction that is going to occur then therefore is going to be picking up of that particular partial positive part of that molecule, and this is going to result into the formation of what we call a second degree carbocation, which basically is going to look like this. So it's going to have a formal charge at that particular point, whereby if you try to look at this, we're going to see that this particular second degree carbocation is unstable, and therefore it will have to undergo the next stage in order to form a final product. So we had said that this particular electron-rich part is going to be contact, so therefore this is going to act as a leaving group, and from this particular case, therefore we're going to have this particular bromide ion in this second stage, whereby it is going to be contact or attack on that specific part of the secondary carbocation, and this is going to lead to the formation of a final product, whereby we are going to have this one as a bromide group having those two bromine atoms attached at that specific point. So therefore this is going to form the final product of that electrophilic, particularly the halogenation process of this simple reaction for the electrophilic addition in this particular case. And we're going to consider some cases whereby we're going to see the aspect of the concept of stability. And we had mentioned earlier in our first video that there is an order of preference insofar as stability is concerned whenever you are trying to consider the aspect of the first degree, second degree, and the third degree carbanium ions. So in this case, we are going to consider also a case whereby at this specific point there is going to be two specific steps. This is the interaction between the electron-rich alkane functional group parts and then the halogen, whereby there's going to be this particular electrophilic reaction taking place. And therefore, in this particular case, at the second stage, there is a tendency of this particular intermediate form trying to form what we call a halogen ion. And this case, that particular kind of ion, we can be able to, in our case, in the order of bromine, if we are using bromine as our molecule to illustrate this, then we are going to have what we call a bromonium ion, which is going to form an intermediate ion in this particular case. Now we're going to show that one using a reaction mechanism perhaps of our second illustration. But in this case, from this particular stage, I can just give an example and try to show how that specific ion is formed. So let me just do away with this. So I've said that the interaction between the bromide group and the electron-rich alkane functional double bond is going to result in the formation of this secondary degree carbocation, which is having a formal charge at that specific point. So in some cases, there's a concept of there's going to be a formation of an halogen ion, which I said is a bromonium ion. Basically, this is due to the concept of stability. So therefore, in this case, this is going to just do a rearrangement with that, and this is going to form that particular ion, which we said can have a preference of this resonating between these two particular states. So this is going to have this bromonium ion appearing also. This is a bromonium ion. This is going to have this bromonium ion appearing as such. So in this particular case, we are also going to consider the case whereby there's going to be rearrangement, and this is going to lead to the formation of a third degree carbocation, which is basically going to be particularly stable. Now we can just look at an example in this particular case of perhaps a cyclohexane, and then try to see how that reaction is going to take place and the subsequent rearrangement that is going to be experienced, and so far as a combination of this specific cyclohexane is concerned, cyclohexane is concerned. So from that particular illustration, then therefore we're going to see that if this process of halogenation takes place with this kind of a molecule, we're going to have this molecule illustrated as such, and therefore it's going to form a cyclohexane, cyclohexane, and this is a cyclohexane which has undergone bromination. Now, as we have already illustrated from our first case, we shall have this bromide, or rather the bromine molecule, showing that specific bond at that, and the interaction between this double bond, which is electron rich, and this one will lead to repulsion, which will lead to the formation of partial charges at those specific point, and therefore this polarized molecule will be attacked by this double bond, and this of course is going to move in that specific direction. So therefore this will form an intermediate carbocation, basically, which I've referred to a third degree carbocation that is going to have this specific charge at that particular point. So this is going to be a methyl group, and this is a carbocation which has been formed, and therefore the bromide group will be attached at that specific point. Now, bearing in mind that the third degree carbocation is more stable than the second one, then therefore that is going to have a preference for formation. So if you try to consider this aspect of stability, as I've said, therefore this bromide molecule, this bromide ion is going to specifically attack this specific point for the 30 degree carbocation, and therefore this is going to lead to the formation of this final product at that specific point. So in a summary, basically that is going to show the reaction mechanism of this particular case, and this is going to give us a contrast between the second degree carbocation that was forming the aluminum ion and this one. So in case we come across this particular case whereby there is going to be a preference, then therefore we are going to include an aspect of rearrangement for some of the molecules that we're going to see. Now there's this unique tendency that I wanted us to try and discuss, basically, which has a slight relationship with that particular concept for the formation of aluminum ion, but it's going to be dealing with the aspect of rearrangement, which we're going to see being displayed in some of the reactions. So I had said that we can be able to illustrate these particular molecules in 3 dimensions as this, whereby we're going to use wedges and those specific illustrations, which is going to appear as such. So therefore, if we try to consider this particular molecule, if this one is undergoing halogenation, then therefore just going to have it in our space. So we're going to have this molecule being given as such, and therefore this is going to be given like that. So I'm trying to consider this specific case of this ion, whereby this double bond is going to be on this, and this is going to move. And therefore, from this particular case, we're going to see that the subsequent intermediate step, intermediate species that is going to be formed is going to have this bromine molecule being arranged as this. So we're going to have an intermediate whereby this bromine molecule is trying to bond with these 2 carbon atoms that we are having a sigma bond, and therefore this is going to lead to the formation of this particular case, whereby we are going to have this bromide ion having a positive charge. This is a positive form of charge at this specific point, and if we try to look at this, then therefore we had said that the bromide ion is going to attack this specific molecule in order to form a stable one. Therefore, we are going to see that it's going to attack this specific point, whereby we have a carbon bromide sigma bond, and this is a carbon bromide and sigma antibonding molecule, whereby it's going to, or rather antibonding molecular orbital, whereby we are going to see that it's going to attack at this specific point, and this is going to move, and therefore we are going to have a final product being given as this one. The space is going to be enough. So we had earlier mentioned on the concept of cis and trans, and we're going to see also the display of this particular case, the orientation of this molecule. So if I try to put this one as such, so this is going to be a bromide, and then we are going to have this one displayed as this is a wedge, and then therefore we are going to have another one being given as such, and therefore we're going to have a final product that is going to appear as that, and this is the effect of the bromonium ion, which is going to try to dictate. We have talked about the order of the preference for this specific case for stability, and therefore it's going to play a role in this particular case for the this bromonium ion this specific point. So therefore the interaction between these two carbons in an essence is due to the large nature of the bromide molecule as molecule compared to the chlorine one, and we are going to see the formation of an instant sigma bonding that I've said, of course, which is a carbon bromide, of course, a sigma bond at this particular point with the interaction of both the two carbons that formed the double bond of the alkyne functional group. So in this particular case, of course, we had mentioned earlier that we are going to consider the case of a rearrangement, whereby basically the rearrangement is going to occur in order to form what we call intermediate species, which basically are going to result also in the formation of a stable product, as we have already illustrated in the last two cases of our discussion for this. So basically the concept of halogenation reaction is going to entail the interaction of these specific molecules that are said with their alkane functional group, and we're going to have more examples of our illustration as we go by in our various discussions, especially in the concept of organic reaction mechanisms that we're going to see later in some of our videos. So that is it for now, guys. Catch us in our next video, and kindly check on our description boxes for various links to other related videos, especially on these various topics. So we're going to have a continuation of these reactions, whereby we're also going to consider, apart from us having looked at the concept of hydration, which we said that takes place under the strong acidic condition, we have also looked at the concept of halogenation, whereby we say that the double bond is going to react on the halogen molecules in order to form. And also from this particular discussion for today, we have looked at the formation of some of the intermediates and the preference for this particular case for stability, whereby we say that third degree carbocation, second and third have a preference, or the point of interaction insofar as this one is concerned, and therefore this one will have preference, and therefore there are some rearrangements that we are going to see later, which are going to happen in order to cater for this aspect of this particular case for the third, second and first degree carbocations. So that is it for now, guys. Bye. God bless you.